Hi everyone, and welcome to our last chemistry video tutorial. We've made it through the unit. Next week we'll be focusing on a unit task, so it's going to be a bit of an opportunity for you guys to show me what you've learned this unit. I know we're missing sort of that hands-on lab approach that I would usually love to take in chemistry, but I hope that you found these videos okay so far and that you've been able to learn some stuff from them. So this is our last one. Let's grab the note that goes along with it and we'll jump right in. We're going to be talking about acids, bases, and neutralization reactions. So before we go too far, we need to just sort of pause and understand water a little better. So as a liquid, water tends to dissociate, and that means break apart into hydrogen ions and hydroxide ions, so H plus and OH negative. And so it likes to break apart, and that's just kind of how it likes to hang out. If you were looking at a glass of water, you'd really be looking at a whole bunch of these H plus ions and these OH ions. It doesn't typically like to hang out together as a full H2O molecule. It likes to break apart. And so because we have an equal amount of OH and H's in water, we call this neutral. And we're going to get into what that means, what pH is. We're going to talk about all that today. But just know that when we look at a glass of water, we're looking at these separate hydrogen and hydroxide ions swimming around, and that because we have an equal number of each, we have a neutral solution. And so if we look down here at this sort of dissociation, this breaking apart of those parts of water, we're going to be talking about how the H plus is what ends up being called an acid. And this OH negative is what ends up being called a base. If we have something that produces these H pluses, it's an acid. If we have something that produces these OHs, it's going to be a base. So let's go through and we'll dive a little deeper into each of those. So we'll start with acids. So like I kind of just said, the substances that produce hydrogen ions, or H pluses, in solution are called acids. And so any solution that is acidic is going to have more H pluses than it does OHs. So all of a sudden we're no longer balanced. We've got a lot more H pluses in here than we do OHs, and that's what makes something acidic. So if we compare some properties of acids, if we look at physical properties, acids can conduct electricity, they're electrolytes. They typically taste sour, so you can think of some citrus fruits that taste sour, those are all acidic. And they're water soluble, so they can be dissolved in water. So we've got some pictures here, we've got stomach acid, vinegar, these might be common acids that you've heard about. Naming acids. This is the last time I am going to throw new naming rules at you guys. So just pay attention here, and this is the last one you've got to know. So there's two types of acids. The first one is called a binary acid, and it's called binary. Every time we see that prefix bi, it means two. So binary acids contain only two elements. We've got hydrogen and another non-metal. And so the naming rule for binary acids is we're going to say hydro blank ic acid. And so this blank would be filled in by whatever the non-metal, the other non-metal is in the compound. So if we look at some examples, that might make a bit more sense. So if I see HF, first of all, I know that that's a binary acid because there's only two elements. There's only hydrogen and fluorine. So HF I would call hydrofluoric acid. So that hydro is what we start with. We fill in the blank with whatever the other element is. We add ic and then acid. So hydrofluoric acid. If I have HCl, then that would be hydrochloric acid. So that's the naming rule for binary acids. Our other kind is called oxyacids. And so oxyacids contain a hydrogen and a polyatomic group that contains oxygen. And so to name these, we don't put hydro. So that's really the only difference. We're still going to fill in this blank by the element in the compound that is not hydrogen and not oxygen. Again, that's going to make a little bit more sense when I give you the example. And then we still have the ic and we still have the acid, but we just are not going to start with hydro. Hydro we only use for binary acids. So what do I mean by that? If I look at this one where I've got H and then I've got a polyatomic group, I've got phosphate here. So for the name, I don't care about the hydrogen, I don't care about the oxygen. What I care about is whatever that other element is. So this would be called phosphoric acid. I don't need the hydro. This next one, I've got hydrogen, sulfur, oxygen. So again, don't care about the hydrogen and oxygen to name this. This is just going to be called sulfuric acid. Okay, let's move on to bases. So bases are substances that produce hydroxide ions in solution. So you can see that a basic solution, like the one in the picture here, has a lot more OH ions than it does H ions. So we've tipped the balance the opposite way now. And so that's what a basic solution is, when we have a lot more of these hydroxide ions being produced than the H pluses. So if we compare the physical and chemical properties, same as acids, bases can conduct electricity. They're typically slippery to touch. They're water soluble, they can be dissolved in water, and they usually taste bitter. So acids usually taste sour, bases usually taste bitter. Chemical properties, they can be very corrosive, and that means that it can burn your skin. And they're often used as cleaning products, and you'll see those warning labels. Here's an example, Drano. You'll see those warning labels on there being like, do not touch to skin, because a lot of bases can provide really serious chemical burns. We often think of acids as being the thing that's going to burn something, and it can, but typically basic burns are actually worse. So that's something to keep in mind when you're cleaning around the house. Always make sure to check those labels. Another chemical property is they can denature proteins and digest fats. So that means within the cells of bodies, they can actually get in there and they can denature proteins, which means to make them, to essentially kill the protein off, which isn't good. That can kill cells. And that's actually why they're slippery to touch, is because they can be killing cells in your fingers. And then lastly, they react with acids to make neutral solutions. So we're going to get to that in a second, what that actually looks like. Naming bases is super easy. We have already done this. This is nothing new. So first of all, most bases are an ionic compound. Ding ding, hopefully that word rings a bell. It's an ionic compound that contains a metal and a hydroxide polyatomic group. So our naming rule is exactly what we already know in terms of polyatomics, how we name those. We're just going to name it based on whatever the metal is, and then hydroxide. So, and hydroxide is one of those polyatomics that's on the chart of the back of your periodic table. So this is exactly what we have done before. So for an example, if we have NaOH, we're going to fill that blank in with whatever the first element, whatever the metal is there. So sodium hydroxide. This one, aluminum hydroxide. So hopefully that is still familiar. If you need to go refresh the polyatomics, then you can always do that. Okay, so the pH scale. This is something you might have heard of. If any of you have pools or hot tubs, or been to pools or hot tubs, you maybe have heard of this, because the pH of those is really important to keep us safe when we're swimming. So the pH scale, or the power of hydrogen scale, is used to measure the concentration of hydrogen ions in a solution. And so it's a logarithmic scale that ranges from 0 to 14, and it tells us how acidic or how basic a solution is based on the concentration of H plus ions. So anything from 0.0 to 6.9. So if I look at my scale, it starts at 0. If I go all the way up to just before 7 here, everything on this side is acidic. So this whole side means that there's more H plus ions than OH ions in my solution. If I go right at 7, 7 is the magic number of the pH scale. So 7 is completely neutral, and that means there's an equal amount of H plus and OH ions. And then on this other side here, so if we go just above 7 all the way up to 14, the end of our scale, that whole end is basic. And so everything here means that there's more OH ions than there are H ions. So here's another look at the pH scale. I liked this one because it kind of really nicely showed us what the pH of some kind of common household things are. So just something to note is the further that you get away from neutral, the stronger the acid or base becomes. So remember, neutral is 7 here, that's pure water. If I start to move slowly to the left, I'm in the acidic territory, and I'm going to be getting stronger and stronger the further away I get. So 0 is the strongest acid we can possibly have, whereas 6 is not a very strong acid. If I go the other way, if I start at that magic number 7 and I start to go slowly to the right, I'm getting more and more basic. My basic solution is getting stronger and stronger and stronger. So 14 is the strongest base I can possibly have. So kind of neat to look at this. You can always pause and check out some of these pictures. Stomach acid is super, super acidic. That's why if you ever have heartburn, it means your stomach acid is coming up a little bit into your esophagus and you feel that burn feeling. Very strong acid. Milk, not so strong. We've got some bleach, oven cleaner. That's the stuff where you'll start to see labels on there to be careful because those are very strong bases. Soap is only slightly basic, enough to kill off bacteria and other stuff. So yeah, so there's kind of a picture of some everyday stuff on a pH scale. So here, this should be on your note. I want you guys to pause. Just try to practice this. Make sure that you have this down, that you know whether this is acidic, basic, or neutral, each of these pHs. So just pause the video right now. See if you can fill out the chart without looking at anything else, and then come back. Okay, so here are the answers. So again, everything above 7 is a base, and everything below 7 is an acid. And 7 is the magic number. That is neutral. And so you can see I put a little star beside these two because I wanted to show what the strongest base and acid in this list were. So if I look for the strongest base, I'm looking for the highest number. And if I'm looking for the strongest acid, I'm looking for the lowest number. So just kind of keep that in mind. Okay, detecting acids and bases. So most acids and bases are clear and colorless. So it can be really difficult to tell what it is you're looking at unless you have something that's labeled. But if you were just looking at a clear colorless liquid, you wouldn't necessarily be able to easily tell whether or not it's an acid or a base. So we can use something called an indicator to tell us if the solution is acidic or basic. And an indicator is a chemical that changes color when it is dissolved into an acid or a base. So a few common types of indicators are blue litmus paper. So blue litmus paper turns red in acidic solution. So you can see the picture here. It's just like a tiny strip of paper. But here you can see that a little drop of acidic liquid solution must have been dropped here because it turned red. So blue litmus paper turns red in acid. And then the exact opposite, we have red litmus paper that turns blue in basic solutions. So this paper started off red. If we drop a little bit of base here, you can see that it turned blue. There's also lots of solution indicators or liquid indicators. So phenolphthalein is one, and it turns pink in basic solutions. So you can see, be able to tell if you have an acid or a base, whether or not it turns pink. There's lots more, by the way. Those are just some of the common ones. So then we have the master of all indicators. This is the best one to use. This is called universal indicator. And most indicators that we just talked about will tell you whether a substance is acidic or basic, but it doesn't necessarily tell you how acidic or basic. So that is the cool thing about this. That's why it's the master of all indicators. Because universal indicator, either the liquid or there's a paper version, can tell you how acidic or how basic a solution is. It can tell you the exact pH, which is really useful. So what you do is you compare, you either drop a few drops of universal indicator into a solution, or you use this paper and dip it in, and then you can compare the color to a chart to determine the pH. And this I'll bring back to our pool or hot tub example. If you are taking care of a pool or hot tub, you have to do this quite frequently to be able to see if you need to adjust the levels or add anything in to keep a safe pH to swim at. So let's watch a quick video that shows how this works, because it's pretty cool.
So first I'm going to start by adding a compound that's a base, sodium hydroxide, into this water. So I'm going to add some sodium hydroxide. And this means that we will start with a basic pH, so something greater than 7. So then I also have a compound that we call the universal indicator, and I will add some of this in. So we can see this nice purple color first tells us that we have a basic pH in our solution. So I'm going to mix this up to make sure that our purple color is fully incorporated, and this means that we have a homogeneous solution, so we have the purple everywhere. So what I'm going to do is I'm going to take some dry ice, which has the chemical formula CO2, and I'm going to add some into this solution. So we can see that the dry ice solid is turning into a gas. So this is a concept known as sublimation, where a chemical goes directly from the solid phase to the gas phase without ever going into the liquid phase. So we can also see that we have these really nice color changes from the initial purple to kind of a blue, a green, and now we're finally at yellow. So each of these color changes indicates a change in our pH. So we started with a basic pH, and now when the carbon dioxide reacts with water, we're able to form carbonic acid, which gives us an acidic pH. Thank you for watching.
Okay, so we're going to bring it back to our lesson from earlier this week when we were talking about types of reactions. And now we can get a better understanding of what exactly a neutralization reaction is. So remember that really all we said about it earlier this week was that a neutralization reaction is when an acid and a base combine to form a water and a salt. And so just a little side note there, a salt is the combination of the cation from a base and an anion from an acid. It doesn't always mean table salt. So it can mean table salt. We're going to go through that example in just a second. But when we say a salt in chemistry, it does not always mean like an edible table salt, okay? So why are these reactions called neutralization reactions? It's because the pH of the product is usually pretty close to 7 or close to neutral. So we're basically going to be combining an acid and a base to create a neutral solution. So An example of a neutralization reaction would be if we started off with hydrochloric acid and sodium hydroxide, we're going to be producing water and sodium chloride, which actually is table salt. So we're going to be producing, and if we look at those two things, both water and table salt are neutral. So we've combined an acid and a base to produce a neutral product. And then this is just sort of one final note on this, is that to fully neutralize a solution, to get that pH 7, both the volume and the strength of the base and acid, those are both important. So we have to look at so we'll go through some scenarios here to kind of make a little bit more sense. So if the acid and base have the same strength, meaning that they're both, the pH is the same distance away from 7, it would take the same volume of each to achieve a neutral solution. So if I started with an acid at pH 4, a base at pH 10, those are equal in strength, so I would need the same amount of each to create that neutral solution. If the acid is stronger than the base, it would take more base to achieve a neutral solution. So if I have a really strong acid, I don't need a lot of it to be able to neutralize this. And then the exact opposite is true as well. If the acid is weaker than the base, it would take more acid to achieve that neutral solution. So if my base is super strong and my acid is kind of medium, then it's not going to take a lot of that base to be able to neutralize that solution. So you don't need to memorize this or think too hard about this. Just wanted to put that out there, that if you're ever doing these neutralization solutions, you're trying to neutralize something, you have to think about the strength of them, and that'll determine how much you actually need to add. Okay, so I know that was a little bit of a longer one, but it is our last one. So that's exciting. There's a few questions or practice questions that I have put up on Google Classroom as well, so give those a try, and I will post the solutions as well so you can check your answers. Awesome job, guys, for making it through these chemistry lessons. Stay tuned for that task that we'll be doing next week, and have a great day.